Imagine peering right into the heart of a star, yeah. Witnessing these nuclear furnaces forging elements and then watching that same star explode with just unimaginable power. What if you could get a shortcut, a real deep dive into understanding these cosmic spectacles, but without getting totally lost in all the jargon? Well, this deep dive is all about massive stars, the giants of the cosmos. They live fast, die young, and profoundly shape the universe around us. Our mission today is to unpack the really intricate science of how these stars evolve, the nuclear reactions that power them, and of course, the dramatic ways they end their lives. Supernovae, black holes, all that good stuff. We're going to dive into the latest research, pull up the most important nuggets of knowledge about stellar modeling and the cutting-edge physics used to understand these, extreme objects. We're drawing from a fascinating review on massive star modeling and nucleosynthesis, plus some new insights into supernova equations of state and the pre-supernova evolution of these stellar titans. Okay, so let's unpack this. Massive stars, they're much rarer than smaller stars like our sun, right?
Oh, much rarer, yeah. But they're absolutely key drivers of cosmic evolution.
Key drivers how?
Well, they leave this huge chemical and kinetic imprint on their surroundings. All the heavy elements they create and then eject.
Right, the elements that make up planets and us.
Exactly, and they dominate galaxy spectra with their intense luminosity. You can even use them to trace star formation way back in the early universe. And it's incredible because for a long, long time, our understanding of these rare, really powerful objects relied mainly on theoretical stellar models. Just math, basically.
Just theory.
Pretty much. But over the last couple of decades, these large observational surveys have started giving us crucial data, real-world constraints.
So we can finally check the models against reality.
Precisely. It highlights where our models shine and, frankly, where they still need some work.
And it's not just observations helping, right? You mentioned computation.
Oh, absolutely. Computational power is accelerating everything. We're talking about these incredibly sophisticated 3D hydrodynamical simulations.
3D, wow. Not just simple 1D lines.
Right. And these 3D sims are providing incredibly detailed recipes, you could call them, for the simpler 1D models that actually simulate a whole star's lifetime. Because simulating a full star in 3D for millions of years, that's just not feasible.
Okay, so we use the detailed 3D snippets to inform the big picture 1D models. Makes sense. And at the heart of it all, you've got these fundamental equations. Stellar structure is famously described as a long and desperate struggle against gravity.
That's Eddington's phrase, yeah.
Classic. And he gave us those 4 core equations.
Yeah.
Hydrostatic equilibrium. That's pressure balancing gravity, right?
Yep. Then mass continuity, how mass is distributed. Energy conservation, where the energy comes from and goes. And radiative transfer, how heat moves through the star.
Those 4 pillars. Plus, you need something called an equation of state.
Right. That just links pressure, temperature, and density. It tells you how the star stuff behaves under different conditions.
So applying these equations must be the challenge, especially for these massive stars.
It is, because the conditions are so extreme and things aren't always nice and symmetrical like the 1D equations assume. Turbulence, rotation. It gets complicated.
Which brings us to a key question. Why are massive stars so different? What makes them giants?
Yeah, that's fundamental. It really comes down to their internal conditions. If you picture a graph plotting temperature against density.
Okay, temperature versus density.
A star's core evolves along a specific path on that graph. Now, low-mass stars, say below 2 times the mass of our sun, their cores become degenerate. That's a quantum pressure state right at the end of hydrogen burning.
Degenerate, okay.
Intermediate mass stars, maybe 2 to 10 solar masses, they hit degeneracy after helium burning. But the massive stars, the ones over 10 solar masses,
They're different.
they manage to burn through all their nuclear fusion phases, hydrogen, helium, carbon, oxygen, all the way to iron before their core becomes degenerate.
So they never hit that quantum speed bump until the very end.
Exactly, and that allows them to just keep contracting, getting hotter, igniting the next fuel source, leading to this unique, really rapid evolution compared to smaller stars.
Okay, so that difference in their core evolution path explains their unique lives. So how does this translate into cooking up new elements, the nucleosynthesis part? They start with hydrogen fusion, like all stars.
Right, the main sequence.
But you're saying it's different in massive star.
It is. They primarily use what's called the CNO cycle. Smaller stars mostly use the proton or PP chain.
So, carbon, nitrogen, oxygen.
Exactly. Those elements act as catalysts. It's still hydrogen turning into helium, but using C, N, and O to help it along, like a cosmic recycling plant, as you said earlier.
And the key insight here is
The CNO cycle is wildly more sensitive to temperature than the PP chain. Exponentially more sensitive.
so hotter cores mean much, much faster burning.
Precisely. That's why massive stars are so luminous and burn through their hydrogen fuel so quickly. It sets the stage for everything that follows.
And what follows immediately after hydrogen runs out in the core.
Well, the core starts to contract, gets hotter, and hydrogen burning shifts to a shell around this now helium core.
Okay, shell burning.
And this internal shift causes a dramatic change at the star's surface. If you plot the star on an HR diagram that's luminosity versus temperature, you see this characteristic hook.
A hook.
Yeah, the star briefly gets a bit hotter at the surface before it rapidly expands and cools, heading towards becoming a red supergiant.
So the core contracts, but the outer layers expand. That seems counterintuitive.
It does. It's this mirror behavior, and it's actually been a point of debate among astrophysicists for a long time. Why exactly the envelope puffs up so much when the core shrinks? It's a complex interplay.
Fascinating. Okay, so after the hydrogen burning phase, the star's now got this helium core. Maybe it's a red supergiant. What's next on the cosmic menu? Helium burning.
Yep, helium ignition. Once the core gets hot enough, around 100 million Kelvin.
And that fuses through the triple alpha reaction.
That's the one. 3 helium nuclei, which are also called alpha particles, combine in a 2-step process to form a carbon nucleus.
And this reaction is sensitive to temperature.
Unbelievably sensitive. The rate goes something like temperature to the power of 41.
41. Wow. Okay, so tiny changes in temperature have enormous effects on the energy output.
Absolutely huge. And what's truly remarkable here, almost serendipitous, is the role of a specific energy level, a resonance, in the carbon-12 nucleus.
The resonance.
Yeah, it was predicted by Fred Hoyle back in the 50s. He realized that without this specific energy level in carbon, the triple alpha reaction would be way too slow. We wouldn't get much carbon in the universe.
So without that lucky resonance, maybe no carbon-based life.
It's a mind-boggling thought, isn't it? Now, there's another crucial reaction that happens during helium burning. Carbon-12 can capture another helium nucleus to form oxygen-16.
Carbon plus helium makes oxygen, okay?
And here's a critical nugget. The more massive the star, the higher the core temperature during helium burning, and the more of that initial carbon gets converted into oxygen.
So the final CO ratio depends on the star's mass.
Heavily. And this final carbon to oxygen ratio is absolutely vital. It dictates how compact the core will be later on, which ultimately influences whether the star can even explode as a supernova or just collapses.
And you're saying the rate of that C to O reaction is uncertain?
Still one of the biggest uncertainties in nuclear astrophysics, yeah.
Yeah.
A subject of intense experimental and theoretical study. Get that rate wrong, and your stellar model can go way off track.
Wow. Okay. And helium burning isn't just about carbon and oxygen, right? There's other stuff happening.
Definitely. It's also a key site for the SES process, the slow neutron capture process.
Building heavier elements beyond iron.
Well, up towards iron, but slowly. Basically, nitrogen left over from the CNO cycle gets converted into neon-22. This neon-22 can then capture an alpha particle.
The helium nucleus.
Right, and that reaction releases a neutron. These neutrons then get slowly captured by other existing nuclei, gradually building them up into heavier isotopes. Things like sulfur-36, chlorine-37, argon-40, potassium-40. It's a slow, steady buildup.
Okay, so we burned hydrogen, burned helium to make carbon and oxygen, and started this S process. What happens when the helium runs out in the core?
Same story, different fuel. The core, now mostly carbon and oxygen, contracts again, heats up, until carbon ignites.
And after carbon?
Neon, then oxygen, then silicon. It's this rapid succession of burning heavier and heavier elements.
And each stage takes less time than the last, right?
Dramatically less time. We're talking millions of years for hydrogen and helium burning in a massive star. But carbon burning might last only thousands of years, neon burning maybe a year, oxygen burning months, and silicon burning days, maybe even less.
From millions of years down to days. Why the incredible acceleration? It's like the star hits the cosmic gas pedal.
It really does. And the fundamental reason is neutrinos.
Neutrinos, those ghost particles.
Exactly. Once the core temperature gets really high, above about 500 million Kelvin, the star starts producing neutrinos in absolutely massive quantities through various processes. And unlike photons, neutrinos basically just stream right out of the star, carrying away energy.
So it's like a massive energy leak.
A huge energy leak. The star is losing energy incredibly fast via neutrinos, much faster than it's radiating light from its surface. This massive energy loss forces the core to contract and burn its fuel even faster to maintain pressure support. It's a runaway process.
So for a, say, 25 solar mass star, recap the timescales.
Okay, roughly. Hydrogen burning, maybe 7 million years. Helium burning, about 500,000 years. Carbon burning, 600 years. Neon, 1 year. Oxygen, 6 months. Silicon, just 1 day.
1 day. That's insane. And what happens during silicon burning? Is it just silicon fusing?
It's actually more complicated than direct fusion. It's so hot, billions of Kelvin, that high-energy photons start breaking silicon nuclei apart. This is called photodisintegration.
Breaking them down.
Yeah, and then those fragments, like alpha particles, get captured by other nuclei. It's this complex reshuffling of nuclei, a sort of statistical equilibrium process.
Nuclear statistical equilibrium, NSE.
That's the term. And the end result of this whole silicon burning mess is that the core composition shifts towards the most tightly bound nuclei, which are elements around iron, primarily iron-56.
Iron-56, the most stable nucleus.
The most stable. You can't get any more energy by fusing iron. It's the nuclear ash, the end of the road for fusion in the core.
So the star now has this inert iron core.
An inert iron core, surrounded by shells still burning, silicon, oxygen, neon, carbon, helium, and hydrogen further out, like a cosmic onion.
The famous onion skin structure.
Exactly. Concentric shells of progressively heavier elements towards the core, often separated by active burning shells. It's this incredibly complex, layered structure that sets the stage for the final collapse.
Right, so this incredible layered cosmic onion is built up. Fusion stops in the iron core. No more energy generation there. Gravity finally wins, right?
Gravity wins. The iron core can no longer support itself against its own weight. And what happens next is, well, the ultimate cosmic spectacle.
The core collapses.
Incredibly rapidly. We're talking fractions of a second. It collapses down from maybe the size of the Earth to the size of a city, reaching densities higher than an atomic nucleus, supernuclear densities.
Wow. And then?
This collapse is halted abruptly when the core material becomes incompressible, basically. It triggers a bounce. The core stiffens and rebounds, sending a powerful shockwave outwards through the infalling outer layers of the star.
The bounce shock, that's the explosion, right?
Well, that was the original idea, but here's the catch. Detailed simulations show this initial bounce shock quickly stalls out. It loses too much energy.
Stalls. Why?
A couple of reasons. Firstly, as the shock plows through the iron core, it actually disintegrates the iron nuclei back into protons and neutrons, which costs a lot of energy. And secondly, those neutrinos we talked about, they're still escaping, carrying away energy from behind the shock.
So if the shock stalls,
Yeah.
that sounds like a pretty big problem if you want a supernova explosion. How does the star actually blow up then?
That is the central question in supernova theory. And honestly, it's still a very active area of research, not completely solved.
Really, after all this time?
Yep. The leading mechanism right now is called the neutrino-driven mechanism, or neutrino reheating.
Okay, neutrinos again. How does that work?
The idea is that even though neutrinos escape easily from the center, the density just behind the stalled shock is so high that a small fraction of the immense neutrino flux coming from the newly forming neutron star does get absorbed there.
So they dump some energy behind the shock.
Exactly. This heats the material, increases the pressure, and can create violent boiling or convection behind the shock. This convective energy, powered by neutrino heating, can then push the stalled shock outwards again and hopefully revive it, leading to the explosion we see.
Convection helps push it out. Are there other factors?
Oh, yeah. Multidimensional simulations, 2D and 3D, show that things aren't perfectly spherical. You can get phenomena like the SASI, the standing accretion shock instability.
SASI. What's that?
It's basically a large-scale sloshing or wobbling of the stalled shock wave. Imagine it sloshing back and forth. This can help push material outwards and might aid the explosion. Plus, rotation of the original star and magnetic fields can also play a significant role, breaking that spherical symmetry and potentially channeling energy outwards.
So it's likely a combination of neutrino heating, convection, SASI, maybe rotation and magnetic fields. A complex mess.
A very complex multi-physics mess, which is why simulating it accurately is so hard.
Now, does every massive star succeed in exploding? What about the really, really big ones?
That's another key question. Observational data is, well, a bit ambiguous for the most massive stars. We seem to be missing the identified progenitors, the original stars, for certain types of supernovae, like type IBC supernovae, which come from stars that lost their outer layers.
Missing them, meaning we don't see bright enough stars disappearing.
Kind of. It suggests that perhaps stars above a certain mass limit, maybe around 25 or 30 solar masses, might not explode successfully. They might just collapse directly into a black hole with no visible supernova, or maybe a very weak one, a failed supernova.
A silent collapse.
Possibly. The debate is definitely not settled on where that mass cutoff lies, or if it's even a sharp cutoff. It might depend on other factors too, like rotation or metallicity.
Okay, so the standard core collapse is one way massive stars end. Are there other kinds of supernova explosions?
There are. In specific mass ranges, we see different mechanisms. For stars at the lower end of the massive scale, say 8 to 10 solar masses.
The lighter heavyweights.
Okay, yeah. They might develop a core made of oxygen and neon, and one core that becomes degenerate. In these cores, electron captures onto magnesium and neon can suddenly remove pressure support.
Electrons getting gobbled up.
Exactly. Less electrons means less degeneracy pressure holding the core up. This triggers a collapse, similar to the iron core collapse, but starting from different conditions. It leads to what's called an electron capture supernova, or ECSN. They're thought to be generally less energetic than typical iron core collapse supernovae.
Okay, electron captures for the 810 solar mass range. What about the really massive end, like way bigger?
Now we get into pair instability supernovae, PISN. These are thought to happen in stars that are initially extremely massive, leading to carbon-oxygen cores somewhere between, say, 30 and 135 times the mass of the Sun.
Carbon-oxygen cores that big.
Okay. If the center of such a core gets incredibly hot, maybe 1 to 2 billion Kelvin, the photons become energetic enough to spontaneously convert into electron-positron pairs.
Light turning into matter and antimatter. Easy 5 volts in action.
Precisely. This process effectively removes photon pressure support from the core, causing it to contract rapidly. This triggers runaway oxygen and carbon burning.
Runaway burning.
Yeah, an uncontrolled thermonuclear explosion that completely obliterates the entire star. No neutron star, no black hole left behind, just gone.
Wow. Complete disruption. That's a pair instability supernova.
That's the standard PISN. There's also a variation for slightly lower core masses, maybe 30 to 60 solar masses, called pulsational pair instability supernovae, or PPISN.
Pulsational.
Yeah, here the instability triggers energetic pulses or explosions that eject significant amounts of the star's outer layers, but don't completely destroy the star initially. It might go through several pulses before finally collapsing, possibly into a black hole.
So multiple bangs before the final end.
Could be. It's a complex scenario.
Now, you mentioned these PISN leave no remnant. Does that have implications for black hole masses?
Absolutely, because PISN completely destroys stars in that core mass range, roughly 30 to 135 solar masses. It predicts there should be a gap in the possible masses of black holes formed from single stars. We shouldn't find black holes with masses, say, between about 50 and 130 solar masses.
A black hole mass gap, has that been observed?
Well, that's where it gets really interesting. The detection of the gravitational wave event, GW190521 by LIGO Virgo, involved merging black holes, one of which had a mass right in that predicted gap around 85 solar masses.
In the gap. So that challenges the PISN theory.
It definitely stirs the pot. It makes us question our understanding of PISN, or maybe suggests alternative formation channels for such massive black holes, perhaps through previous mergers or in very different stellar environments. It also highlights, yet again, how sensitive these outcomes are to uncertain physics, like that carbon alpha reaction rate we discussed. Change that rate, and you change the core structure and potentially shift the mass range for PISN.
It always comes back to those fundamental details. Before we move off supernova, we have to mention SN 1987 there, right?
Absolutely iconic. The supernova in the Large Magellanic Cloud in 1987, it was the closest visible supernova seen since Kepler's star in 1604.
And the crucial thing was?
Neutrinos. For the first time, neutrino detectors here on Earth actually detected a burst of neutrinos coming directly from the core collapse. It was stunning confirmation of the core collapse theory and the immense neutrino emission involved, like feeling the tremors from that cosmic earthquake, as you put it.
Direct evidence from the heart of the explosion.
Yeah.
Amazing. Okay, this whole deep dive really underscores that understanding stars isn't just about looking through telescopes. It's heavily reliant on these incredibly complex numerical models.
Absolutely.
So what are the biggest headaches, the major challenges and uncertainties that stellar astrophysicists are grappling with today when they build these models?
Well, you hit on a key point. The models are fundamentally only as good as the physics we put into them. And a lot of the crucial physics is inherently multidimensional.
Like convection you mentioned.
Exactly. Convection, rotation, magnetic fields, these are 3D processes. But simulating a star's entire evolution in 3D is computationally impossible right now. So we have to approximate these effects in our 1D evolution codes.
Approximations mean fudge factors.
Sometimes, yeah. They often come with free parameters, knobs we can turn in the code. Things like the efficiency of convective mixing or how far convection overshoots its formal boundary. We try to calibrate these parameters against observations like the width of the main sequence on the HR diagram or surface abundances.
But calibrating works for the stars you calibrate against. What about predicting other stars?
That's the worry. How predictive are these calibrated 1D models when we apply them to stars with different masses or different compositions, like stars in the early universe with very few heavy elements? It's a constant challenge.
And beyond the big multi-deep processes, you mentioned even the nuclear reaction rates themselves have uncertainties.
They do. Measuring these rates in the lab is incredibly difficult. We're trying to replicate conditions deep inside stars, billions of degrees, immense densities. We often have to measure at higher energies than are relevant in the star and then extrapolate downward.
Extrapolate, meaning you might miss things.
You might miss crucial low-energy resonances like that Hoyle state in carbon, which can dramatically increase a reaction rate at stellar temperatures. So there are still significant uncertainties, sometimes factors of 2 or even more, on key reaction rates.
That sounds like a big deal. If you change a reaction rate, does it just change how much of an element is produced?
It's more subtle and profound than that, especially if the reaction is a major energy source for a particular burning stage.
How so?
The star actually adapts. If you make a key energy-producing reaction, say, stronger, the star might actually adjust its internal structure to burn that fuel at a lower temperature and density to maintain equilibrium.
Whoa, so it compensates.
It compensates, which means changing the rate doesn't just linearly change the outcome. It can alter the entire evolutionary path of the star, the duration of burning stages, the final core structure, and ultimately the nucleosynthetic yields in ways that aren't immediately obvious.
So that carbon-alpha reaction uncertainty we keep mentioning
Is absolutely paramount for exactly this reason. Its uncertainty directly impacts that crucial CO ratio after helium burning. That, in turn, shapes the subsequent burning stages, affects the size and compactness of the iron core, influences the explodability in supernova models, and can even determine whether a low metallicity star undergoes a PISN or not. It's a linchpin reaction.
in this process. Building heavier elements, also sensitive.
Very sensitive. The main neutron source in massive stars is that neon-22 capturing an alpha particle reaction. That rate has roughly a factor of 2 uncertainty. And the reaction that competes with it, neon-22 capturing a gamma ray instead, is even more uncertain, especially regarding possible low-energy resonances. Tiny changes here can ripple through the calculated abundances of dozens of heavier isotopes.
Okay, nuclear rates are tricky. What about convection? You said it's a 3D nightmare for 1D codes.
It really is. First, there's even disagreement on the best criterion to use to decide where convection happens. The Schwarzschild criterion versus the Ledoux criterion, which includes composition gradients.
Different criteria give different convective zone sizes.
They can, yes. And then how do you model the mixing itself within that zone? The most common approach is the mixing length theory, MLT, which has its own adjustable parameter, alpha MLT, basically describing how far a blob of convective gas travels before dissolving. It's a very simplified picture of complex turbulence.
And the biggest issue you mentioned was overshoot.
Convective boundary mixing, or overshoot, yeah. Standard models using just MLT often predict convective cores, especially during hydrogen burning, that seem too small compared to what observations suggest.
Too small. How do we know?
From things like the width of the main sequence band in star clusters. To match observations, models generally need more mixing than the basic theory provides. So we add prescriptions for overshoot, where convective elements penetrate or overshoot into the formally stable radiative layers above the core, mixing extra fuel in.
More parameters to adjust.
More parameters, yeah. How far does it overshoot? How efficient is that mixing? Different codes use different recipes. Thankfully, those multi-D hydrodynamic simulations are starting to give us better physical guidance, providing actual recipes for how this boundary mixing works, which we can try to implement in 1D codes.
So 3D sims help calibrate the 1D approximations.
Hopefully. Those sims are also revealing other complexities, like convection exciting internal gravity waves at the boundary. These waves can travel through the star and transport angular momentum, which is important for understanding stellar rotation.
And another recent finding from simulations, shell mergers.
Yes, this is fascinating. Multi-D simulations and now even some advanced 1D models incorporating insights from them show that different burning shells can actually merge together very shortly before the core collapses.
Like the oxygen shell running into the neon or carbon shell.
Exactly. These mergers can drastically change the composition of the material just outside the iron core right before the explosion. This seems to explain some observed abundance puzzles, like why supernovae sometimes produce unusually large amounts of elements like phosphorus, chlorine, potassium, and scandium. It also affects the structure right above the core, which can influence the star's explodability. It makes the pre-supernova star a very dynamic place.
Okay, internal mixing is complicated. What about rotation? Stars spin, don't they?
Most do, yes, and rotation adds a whole other layer of complexity.
How does it affect the star? Just flattened a bit.
Well, the centrifugal force does provide some extra support against gravity, so a rotating star effectively acts a bit like a slightly less massive non-rotating star. But the really important effect is internal mixing driven by rotation.
Mixing again. How does rotation cause mixing?
If the star isn't rotating uniformly, if different layers spin at different rates, which is expected, this differential rotation can drive instabilities and large-scale circulation patterns, often called meridional circulation. Think slow. Large currents moving material up and down and horizontally within the star.
And these currents transport chemicals, angular momentum.
Both. Transporting chemicals is key. It can dredge up fresh hydrogen fuel into the core, making the hydrogen burning phase last longer. It can mix nitrogen produced in the core out to the surface. It can significantly alter that crucial CO ratio we keep talking about.
So rotation changes the nucleosynthesis.
Definitely. And it affects the star's evolution on the HR diagram. In some extreme cases of very fast rotation, the mixing can be so efficient that the star evolves almost chemically homogeneously, meaning its composition stays uniform throughout. These stars might bypass the red supergiant phase entirely.
How do we test these models of rotation? Can we see the mixing?
It's tough. We try to use surface abundances. For instance, seeing enhanced nitrogen on the surface of a massive star is often taken as evidence of rotational mixing, bringing CNO cycle products up from the interior.
So fast rotators should show more nitrogen.
It's often assumed, but reality seems more complex. Observations show the relationship isn't simple. The amount of enrichment depends on mass, age, maybe binary history. It's not just about spin rate. Our best hope for directly probing the internal rotation is astroseismology.
Studying starquakes, stellar oscillations.
Exactly. The frequencies of stellar oscillations are sensitive to the internal structure, including the rotation profile. We're starting to get data, especially from space telescopes like Kepler and TESS, but we need much more, particularly for massive stars, to really constrain the models.
Is there a mismatch between models and observations for rotation?
There's a significant one known as the fast core problem. Stellar evolution models that include rotation often predict that the iron core just before collapse should be spinning very rapidly. But when we observe young neutron stars, the pulsars formed in supernovae, they're generally spinning much slower than predicted.
So the core somehow slows down.
Something has to slow it down. Either there needs to be much stronger coupling or angular momentum transport between the core and the outer envelope during the star's life than our current models include, perhaps via magnetic fields, or maybe the supernova explosion mechanism itself somehow manages to slow down the nascent neutron star significantly. It's a major puzzle.
Rotation, mixing. What else? Stars lose mass, right? Stellar winds.
Hugely important. Massive stars have powerful winds throughout their lives, and they shed a significant fraction of their initial mass.
How much mass are we talking?
It varies, but a very massive star might lose more than half its mass before it dies. The winds are different at different stages. Relatively thin, but fast winds when they're hot blue stars on the main sequence. Much denser, slower winds when they're cooler red supergiants. And then extremely dense and fast winds if they become Wolf-Rayet stars.
Wolf-Rayet. What are those?
We'll get to them. But this mass loss is critical because it affects the star's evolution, its final mass, the size of its helium core, the size of its iron core, and ultimately what kind of supernova it produces, if any.
How well do we understand these winds? Can we model them accurately?
It's another tricky area. The winds are driven by radiation pressure pushing on atomic spectral lines, which is complex to model. And observations often give conflicting mass loss rates depending on the technique used, which hints that the winds might be clumpy or inhomogeneous, not smooth outflows like simple models assume.
Clumpy winds.
Yeah, dense clumps embedded in a more tenuous medium. This makes measuring the average rate very difficult. There's even a thing called the weak wind problem for some types of hot O-type stars, where the observed mass loss rates seem much lower than theoretical predictions. So lots of uncertainties here, too.
Is there an observed limit to how luminous stars can get because of mass loss?
There seems to be, yes. It's called the Humphreys-Davidson limit. If you plot luminous stars on the HR diagram, you see this upper boundary. Stars initially more massive than about 40 solar masses don't seem to evolve all the way to become red supergiants.
What happens to them instead?
They likely enter a phase as luminous blue variables, or LBVs. These stars undergo episodes of extremely intense, unstable mass loss. The most famous example is Ea Carinae, which ejected something like 10 solar masses in a giant eruption in the mid-1800s.
10 solar masses in one go.
Huge eruptions. These LBV phases are thought to strip off the star's entire hydrogen envelope, preventing it from ever becoming a red supergiant. Instead, they evolve directly into Wolf-Rayet stars.
Ah, the Wolf-Rayet stars again. So they're the result of extreme mass loss.
Exactly. Wolf-Rayet stars, or WR stars, are essentially the exposed, very hot cores of massive stars that have lost their outer hydrogen and sometimes helium layers. They have unique spectra dominated by emission lines of helium and nitrogen, carbon, and oxygen.
Exposed cores and their spectral types like WN, WC, WO.
They indicate how much the star has been peeled away. WN stars show nitrogen and helium, products of CNO burning. WC stars have lost the WN layer and show carbon and helium, products of helium burning. And WO stars are even more stripped, showing oxygen. They reveal the onion layers from the outside in.
So putting it all together, mass loss dictates the star's final state.
Fundamentally, yes. It determines whether the star dies with its hydrogen envelope intact, leading to a Type II supernova, or if it loses the hydrogen, leading to a Type Ib supernova, or if it loses both hydrogen and helium, resulting in a Type Ike supernova. Mass loss sculpts the star's final appearance and its explosive demise.
Convection, rotation, mass loss. Anything else complicating the picture?
The elephant in the room. Binarity.
Ah, right. Most massive stars aren't alone.
Exactly. A very large fraction, maybe 70% or more, are born in binary or even multiple star systems, and interactions with a companion can completely alter a star's evolution compared to a single star.
How do binaries interact? Just gravitationally?
Gravity is part of it, leading to things like tidal forces that can synchronize the star's spins tidal mixing, but the really transformative process is mass transfer.
One star dumping material onto the other.
Yep. If one star expands as it evolves, say, becoming a red supergiant, it might overfill its Roche lobe, its gravitational zone of influence, and start spilling gas onto its companion star.
When can this happen?
At different stages. We call it case A mass transfer if it happens while the donor star is still burning hydrogen on the main sequence. Case B is after the main sequence, during shell hydrogen or helium burning. Case C is even later, after helium burning.
And the transfer can be messy.
It can be stable, a nice steady stream, or it can be unstable and runaway. Unstable transfer, especially if the donor star has a deep convective envelope, can lead to a common envelope phase.
Common envelope. Sounds cozy.
Not really. The companion star basically gets engulfed by the outer layers of the donor star. The two stellar cores then spiral inwards within this shared envelope due to gas drag.
What happens then? Do they merge?
They might merge, forming a single, rapidly rotating, rejuvenated star. Or the orbital energy released as they spiral in might be enough to eject the common envelope entirely, leaving behind a much tighter binary system, perhaps consisting of the core of the donor star and the original companion.
Wow. Modeling that must be incredibly difficult.
Common envelope evolution is one of the biggest unsolved problems in binary stellar evolution. It's crucial for understanding the formation of many exotic objects like X-ray binaries, gravitational wave sources, and even some types of supernovae, but it's computationally extremely challenging.
So binary interactions just throw a whole new set of wrenches into the works.
Absolutely. They can strip stars, spin them up, rejuvenate them, merge them. It means the evolutionary path of a massive star in a binary can look completely different from that of an isolated star.
Okay, so given all these complexities, convection rotation, mass loss, binarity, uncertain reactions, accurate physics inputs for the models are clearly paramount. Let's switch gears slightly and talk about one specific cutting-edge tool, a new equation of state for supernova simulations. First off, remind us, what exactly is an EOS?
Right. An equation of state, or EOS, is essentially a giant lookup table. It gives you all the thermodynamic properties of matter, things like pressure, energy, entropy as a function of temperature, density, and composition, like the fraction of protons and neutrons.
So it's the rule book for how star stuff behaves under pressure.
Exactly. It's the fundamental recipe book for how matter behaves under the extreme conditions you find inside collapsing stellar cores, neutron stars, black hole formation, and even binary neutron-star mergers. You absolutely need an accurate EOS to simulate these events properly.
And there's a new one based on advanced nuclear physics.
Yes, this particular new EOS table is built using what's called a variational many-body theory, starting from realistic models of the forces between nucleons, protons, and neutrons. It calculates the properties of both uniform nuclear matter and, crucially, the inhomogeneous phase.
Inhomogeneous, meaning not uniform.
Right. At densities below nuclear saturation density, but still very high, matter tends to clump into nuclei surrounded by a gas of neutrons and protons. The EOS needs to describe this complex pasta phase, as it's sometimes called, as well as the uniform liquid phase at higher densities.
Okay, so what's different about this new EOS compared to older ones often used in simulations, like the popular Shen EOS?
One key difference lies in the prediction for the liquid-gas phase transition in nuclear matter. This new EOS predicts a higher critical temperature for that transition.
Why?
It's mainly due to a smaller value of a quantity called the symmetry energy coefficient in this new model, particularly how that symmetry energy changes with density. This parameter basically describes the energy cost of having an unequal number of protons and neutrons.
And that affects the phase transition. Anything else?
It also predicts larger nuclei, larger mass numbers, forming in that inhomogeneous, non-uniform phase compared to older models, so the clumps are bigger.
Interesting. How does it perform when looking at neutron stars, the things left behind by supernovae?
Well, when applied to hot, newly formed proto-neutron stars, this new EOS is generally softer at the lower end of the density range found inside them. This results in slightly smaller predicted masses for proto-neutron stars compared to some older EOS.
Softer meaning more compressible.
More compressible at those specific densities, yeah. But crucially, when you look at cold, fully formed neutron stars, the maximum possible mass predicted by this new EO is consistent with observations of the most massive neutron stars we've found so far.
Like those pulsars nearing two solar masses.
Exactly. PSR J16 and 14, 2230, and J0348 plus 0432. And EOS has to be able to support at least two solar masses, otherwise it's ruled out by observation. This new one passes that test.
Good. And how does it behave in actual supernova simulations? Does it change the explosion dynamics?
In the initial simulations performed so far, during the collapse phase before the core bounces, it behaves pretty similarly to older EOSs, like the Shen model. But right at the bounce point, there's a difference.
What difference?
The new EOS leads to a larger central density and a smaller radius for the inner core at the moment of maximum compression. This indicates that at those very highest densities reached during the bounce, this new EOS is actually softer than the Shen EOS.
Softer at the very peak density.
Seems so, which shows how important the details of the EOS are, especially around bounce, for setting the initial conditions for the outgoing shock wave. A slightly different bounce could potentially influence the later revival of the shock.
So even the fundamental rule book for matter itself is still being refined and has consequences for the explosion.
Absolutely. It's another piece of the incredibly complex puzzle.
Wow. Okay, so from CNO cycle kicking things off fast to the frantic final burning stages, the mysteries of the stalled shock, the PISN mass gap controversy, all the way through convection, rotation, mass loss, binarity, and now down to the nitty-gritty of the equation of state. The life and death of massive stars really is a cosmic ballet of extreme physics.
It truly is. And it's clear that while stellar models have come an incredibly long way, they are absolutely still evolving, still works in progress.
And we can't just, run a perfect 3D simulation of a star from birth to death yet.
Oh, heavens no. That would literally take billions of years of CPU time on the fastest supercomputers we have today. We have to rely on combining different approaches.
So no running that on my laptop then.
Afraid not. Researchers are constantly looking for those clever workarounds, ways to incorporate the insights from detailed short-term 3D sims into the long-term 1D evolution codes. It's about being smart with the computational resources we have.
But the path forward seems clear, even if challenging. What's the strategy?
I think it's really about synergy. Combining the flood of data we're getting from large-scale astronomical surveys, mapping stars across galaxies, finding transients with the incredibly precise measurements of stellar interiors that astroseismology is starting to provide.
Listening to the stars sing.
And using both of those to constrain and inform the theoretical models, especially those detailed multidimensional hydrodynamic simulations that give us the recipes for complex processes like convection and mixing. Each piece informs the others.
Data, internal structure, detailed physics simulations, feeding back into the big picture evolutionary models.
That's the goal. It's an iterative process, constantly refining our understanding.
So let's leave our listeners with a final thought. What does all this complexity, all this extreme physics mean for, well, for us, looking up at the night sky?
That's a great question.
Next time you look up at a star, maybe one that looks particularly bright, consider this. You're not just seeing a point of distant light. You're looking at an object governed by this incredible, complex interplay of forces. Think about the nuclear furnace deep inside, churning out elements.
The unseen torrent of neutrinos streaming out from its core, carrying away energy.
The turbulent convection, the spin, the layers it might be shedding, and that delicate balance that ultimately determines its fate.
Will it end its life with a spectacular bang, a supernova, forging and scattering the very heavy elements that make up planets, life, everything around us?
Or will it perhaps collapse more quietly, directly into a black hole, a silent, dense oblivion taking its secrets with it? It's quite something to ponder.